In this video, I am going through S1, Chapter 4 and Section 4.5 about conditional probability. The probability of an event can change depending on the outcome of a previous event. For example, the probability of you being late for work may change depending on whether or not you overslept. Situations like this can be modeled using conditional probability. You use a vertical line symbol, that's our vertical line, to indicate conditional probabilities. For example, the probability that B occurs given that A has already happened is written as the probability of B, vertical line, A. Basically, this question is saying find B. Find the probability of B given A has happened. Similarly, if you want to find the probability of B given that A has not happened, this is what you write. The probability of B, vertical line, the complement of A. So that's the probability of B. That's asking you to find the probability of B given the complement of A, given that A has not happened. You can solve these problems involving conditional probabilities by considering a restricted sample space. Well, we restrict the sample space as in we say, well, I'm only going to choose from this part of the Venn diagram, or I'm going to choose only from that part of the sample space, the two-way table. And you'll see how that happens. Now, important to know is for independent events, the probability of A happening given that B has happened or given that B hasn't happened is still the probability of A. That's because A and B are independent. They do not affect each other. So whether B happens or B doesn't happen has no effect on A at all. Therefore, the probability of A remains unchanged. In the same way, if you want to find the probability of B given that A has or has not happened, so it's still going to be the probability of B because A has no effect on B whatsoever. Let's have a look and see. The next example is not in your textbook, but hopefully will make this a bit clearer. James records the weather conditions and the times when his train was late. His results are recorded in the table below. Are the events delayed and snowy independent? Well, I want to know the probability of delay, the train being delayed. I also want to know whether the probability of delayed given it is a snowy day is the same. If they are independent, it means that these two have no effect on each other, which means that these two have the same probability. The probability of delayed is exactly the same as the probability of delayed given snowy. That's if they are independent and have no effect on each other. That basically means that the snow has no effect at all on the train being delayed. So let's have a look. Delayed. That's the delayed. That means there are 35 delays out of 365 days. So 35 out of 365. Now we look at delayed given snowy. Well, delayed given snowy is 12. And it's 12 out of 20 snowy days. So the train was delayed 12 days out of the 20 snowy days. These two are clearly different. Therefore, they're not independent. The snow does affect whether the train arrives on time or delayed. Therefore, no, they're not independent. They do affect one another. The weather conditions does affect whether a train is delayed or not. So they have to be the same, identical, to be independent. Okay, let's look at the textbook examples. A school has 75 students in year 12. Of these students, 25 study only humanities subjects, H, and 37 study only science subjects, S. 11 students study both science and humanities subject. Draw a two-way table to show this information. So the first thing we're going to do is draw our table. Two-way table. The simplest thing to do to start a two-way table is to draw a horizontal line and a vertical line. And the very first thing we're going to do is look at humanities. So we've got humanities and sciences, and some study both. So humanities, and I'm going to put the sciences here. Doesn't matter which way you do this. Well, then when you want is to separate. So you want the people who study humanities, the people who don't study humanities, and you want the total. In the same way, you want the people who study science, you want the people who don't study science, and you want the total. And just like in a Venn diagram, you start with the overlap. I would do the same in the two-way table. You are told that 11 students study both science and humanities. So both science and humanities is here. Science and humanities. So I'm putting my 11 there. So I now have humanities, and I know that 25 study only humanities subjects. So only humanities subjects. So I'm going to put that in the humanities column. These are the people who study humanities. Okay? So people who study humanities only means they don't study science. So that's humanities, not science. Can you see that? This is humanities column. Humanities and science together is 11. Humanities only mean humanities and not science. That's what it means. So that's my 25. And then I know that 37 students study only science subjects. So 37 study science. That's the science is here. So 37 here is science and not humanities. So 37 only. I now can start to put some totals. So 11 plus 25, I have a total of 36. 11 plus 11 plus 37 is 48. I know that the total number of students has to be 75 because here it is, a school has 75 students in year 12. That means I can work out what this is. So if I do 75 minus 48, I get 27. So I've worked that out. Every time you have two numbers, you can work out that middle one, 27 minus 25 is 2. And then 37 plus 2 is 39. So I have filled in the two-way table. So you start with intersection, you note the column, that's for humanities, you note the row, that's for sciences, and you fill in what you know, and you put the totals, and you fill the table. So I filled in the table. Then I'm starting to look at the probabilities. So it says, find the probability of the intersection between those who don't study science and those who don't study humanities. So basically they don't study either of them. Well, the overlap is here. Let me get this. It's here. Here's not humanities and not science, and it's 2. 2 out of the 75 students in year 12 don't study either humanities or sciences. So 2 out of the total. The next one says, I want to find the probability that the student studies science given that they are already studying humanities. So the probability that the student studies science given they do humanities. That means that is restricting. That's when I restrict my sample space. It means I am only looking at people in this column. So I'm only looking at the 36 people. These are the 36 people that I know it is given, it is known, that's what given means, it is known that they study humanities. So out of the 36, it changes your denominator. Changes your denominator. You're only choosing. Only from those studying the humanities. So how many out of 36 have chosen science? Well, that's 11. 11 out of 36. And the last one says, find the probability that they study humanities given that they don't study science. So find the probability that they study humanities given that they don't study science. So I need to know where are the people who don't study science. So that are these the people that I'm interested in. So it's out of 27. There are 27 people who don't study science. And out of those, you can see 25 study the humanities. So we restrict the sample space by saying, this is my sample space now. I am only looking at these people because I know that the people I am choosing from do not study science. It is a given, it is something that I know, it is something that I'm told. Okay. And the final example says, 2 4-sided dice are thrown together and the sum of the numbers shown is recorded. Draw a sample space diagram showing the possible outcomes. So because the dice are 4-sided, not 6-sided, they're not cubes, we are assuming that the numbers are going from 1 to 4. So 4-sided dice, we're assuming, unless we're told otherwise, that the numbers are going from 1 to 4. And again, the first thing I would do for my sample space for my two-way table is to draw my vertical and horizontal lines. I will put the plus here because it says the sum, and I'm going to put dice 1 there and dice 2 here. It doesn't matter which way you put it. 1, 2, 3, and 4. 1, 2, 3, and 4. And I am going to add them up. So 2, let's put a different color. Let's put this one. Okay, so 2, 3, 4, 5. 3, 4, 5, and 6. 4, 5, 6, and 7, and 5, 6, 7, and 8. And you can see that it's a 4x4 table, so it may be out of 16 depending on how we restrict the sample space. So that's part A. We've done that. Let me create more space. Okay. And part B says, given at least one dice lands on a 3, okay, find the probability that the sum of the 2 dice is exactly 5. So at least one dice lands on 3. So doesn't matter which one. So at least one dice lands on 3. Could be more. So I'm just getting my pen to work. Could be more, so at least. So I've restricted my sample space because of that word at least. At least 1 means could be 2. So this is where dice 1 lands on 3. This is where dice... no, this is not where dice 2 lands on 3. This is where dice 2 lands on 3. So it's out of 1, 2, 3, 4, 5, 6, 7. And it's 7, not 8, because this is a repeat. So it's the total is 7 outcomes. And I need to find that the dice is exactly 5 and there are 2. This one and this one. So it is 2 out of 7. And then it says, state one modeling assumption used in your calculations. And what have we assumed? Well, we've assumed that the dice are fair, and therefore the probability of landing on 1, 2, 3, or 4 are all equally likely. So whenever we are doing these theoretical working out of probabilities, we are assuming that things are fair, unless we are told that things are not fair and are given specific probabilities to work with. So we're assuming that the dice are fair and all probabilities are equally likely. And that is section 4.5, conditional probability.